lots of good organization, and I think you'll enjoy the next few days and all the information. So for those that don't know me, I'm Bruce DeGennaro, and my role here is just going to be to moderate the event, try to keep us all on time and on track. I'm going to point out just a couple of things as we get started here, and then I'm going to turn it over to others for opening remarks and presentations. Brandon, can you bring up that opening slide just so I can highlight a couple of things there? I don't know if that's something you can do.
Yep, just 1 second. I had closed it. Hold on.
No problem. While Brandon's doing that, I just wanted to highlight there is a Twitter feed. We are in the age of social network here, so you see that right under the title of the workshop here. So hashtag Steelhead Workshop. So feel free to use that as you'd like. Couple of just things to note here: when you come on, you are automatically muted. So if you need to say anything, I don't know if you can unmute yourself or how that works, but I do know that if you have questions, please use the chat. So I think probably the best way to do this is raise your hand if you need to be unmuted for some reason, and or use the chat, and we'll be monitoring that. If you have technical issues, there is an email here that you can use and a phone number that you can use to either call or text. So that's all there for you. I want to just very quickly, I'm going to share my screen if I can do that, and just highlight the agenda. So can folks see my screen okay?
Yes.
Yep, thank you. So this is straight off the council's website. Hopefully you all have been here already. Looks a little bit like this, and this is just an overview. So we do have 3 days planned. We'll start at 9 each day and at 12 each day. And today we'll focus on management challenges and monitoring framework. And then tomorrow we'll talk about historic monitoring and ongoing monitoring. And then on day 3, we'll focus on analytical approaches and the impact of management actions. So everything's broken up into those general categories. And each day we'll have a series of presentations followed by a breakout session at the end of each day, as you see here. I think the timing is the same each day, where we will actually take a break at 11 and then start the breakout at 11:30. And I guess we actually go to 12:30. So the breakouts are an hour long. So, and we'll talk about logistics about how you get into the breakouts when we get there, but we'll pretty much assign you to breakouts and you will magically find your way there. So that's all I wanted to say about the agenda. If you want more details, please go to the website. It's nicely organized here, and there, as you scroll down, you can get all the details for who's presenting what when. So that's there for you as a reference. Again, on the council's website under events, you will find all this good information. So the one other thing I wanted to point out before I turn it over to Luis is that Pascal has created a Mural board, and we will be using Mural, which is an online software for collaboration in our breakouts. So for those that aren't familiar with it, you will be when we're done probably. And but one thing that Pascal has done is created this overall board for the workshop. So I just want to let you all know that it's there, and it's designed to be available to you throughout the next 3 days to enter in thoughts, comments, ideas. It's just a way to capture information from you, another way to capture information. So I'll just zoom in on this a little bit so you can see how it's structured very quickly. So there are some themes across the top here which match the 3 days that I was talking about earlier. There's a management challenges column, a monitoring column, hopefully you all can see that, and an analytical column, and then there's open topics. And then on the y-axis here are some rows And we're just asking for your feedback or thoughts on any surprises relative to these categories, any successes that you feel are worth pointing out relative to those categories. Again, management, monitoring tools, and challenges or information needs. And then in particular, one of the goals of this workshop is really to facilitate partnerships. And so if you have thoughts on partnerships, that would be great too. I'm pretty sure I'm still getting to know Mural, but I think if you just double click in one of these boxes, you get a sticky note, and you can type in that sticky note, whatever you want to say. Okay, and if it doesn't, if you say something you don't want to say, you can hit the delete button and it will go away, and you can make a new one. So I just want to let everybody know that's there. Pascal, I don't know exactly how people get to it though, so I don't know if you're on. We might just mention that. Do you want me to cut and paste this into the chat?
I've moved it into the chat, Bruce. Thank you.
Okay, thank you, Pascal. So go there. I encourage you to use this. It's a great way to just interact and give us your thoughts and information, which of course is what we're all here for. We're here to hear from you as much as for you to hear from the presenters. So I believe that was all I was going to try to cover. So unless there's anything else, Luis, I'm happy to turn it over to you. I guess I can mention we've got 3 opening remarks from Luis, Josh, and Howard Brown, and then we'll get into a series of presentations and then into the breakout. So with that, Luis, happy to hand you the baton.
Bruce.
Sorry. Yeah, Brandon, go ahead.
Bruce, sorry, really quick. It looks like there are 2 people with their hands up. I don't know
I'm sorry. Thank you.
If it was from when you were asking if people could hear you or not. I'm going to unmute them real quick in case they want to be able to.
Thank you. So I've got Michael, and it looks like the only one left standing. So was there something, Michael, you wanted to mention, or was that left over from earlier?
That was like left over. Sorry about that.
Okay, no worries. No, thank you for that. No problem. And Brandon, thanks for catching that. And I'll watch for those hands. Okay, Luis, without further ado, I'll hand it to you.
All right, thank you, Bruce, and welcome everyone to our workshop on monitoring steelhead populations in the San Joaquin Basin. We're really excited to be here today with you. Thanks so much, Bruce, for that excellent intro and orientation. I'm just going to give some brief introductory remarks and then hand it over to Josh Israel from the Bureau and Howard Brown from NOAA Fisheries for some additional context. And as Bruce said, we are tracking this on Twitter. Please feel free to use the hashtag Steelhead Workshop and tweet your own tweets and follow us. So Brandon, please, you can advance. First, I just wanted to talk generally about Delta Science Program independent workshops. They're a really fun and critical way that we try to advance our mission at the Delta Science Program to provide the best possible and unbiased scientific information for decision making in the Delta. And generally our aim in these workshops is to help members of the science, management, policy, and stakeholder communities to gain a shared understanding of the science on a given topic, to help have an opportunity to build trust among each other and partnerships that can then be leveraged to advance needed science moving forward. Next slide. So today, and for the next 2 days, or mornings here, our purpose is really threefold for our workshop. And I just wanted to talk briefly about that. First, and the focus for today is to learn about regional monitoring programs outside of the Delta and the San Joaquin Basin. So we'll be hearing from Greg Sieglitz on the Columbia River Basin and Mariska Obudzinski and Greg Horton from the California Coastal Monitoring Program. And we'll also be hearing from Eric Huber, Devin Pierce, and Will Satterthwaite to understand what we've learned from these programs and studies on the life history variation of O. mykiss and how this work is informing life history models. And so then with this broad context, and on Friday, with a spread of talks each day, we'll be covering monitoring approaches within the Central Valley, as well as analytical and technical tools that we have for informing our decisions and evaluating our management actions. And I think it's important, and you'll see this noted in the agenda for this workshop, that an overriding and theme and just major objective that we have throughout the agenda is to help advance partnerships that can support a sustainable and collaborative steelhead monitoring plan for the San Joaquin Basin. And you'll hear more context on that from Josh and Howard coming up in just a few minutes. So go ahead, next slide. I wanted to take a moment to highlight the really high quality fact sheets that you all received prior to the workshop. A group of scientists and managers supported by the planning committee developed these, and they're very readable. And I really enjoyed the less than 2 hours that I spent. That was all that I needed to read through and really get up to speed on the regulatory background and status of Central Valley steelhead, its incredible life history variation, as well as a summary of the current monitoring support for mykiss in the Central Valley. All the fact sheets were collaborative efforts with multiple authors that in total represented 7 different agencies. So I'm just gonna give an example of why this was so valuable for me to read these workshops in advance, the fact sheets in advance of the workshop. This figure here is from the Distinct Population Segment fact sheet that was produced by Brian Elrott, Howard Brown, and Rachel Johnson of NOAA Fisheries. And it's showing you the 4 Central Valley diversity groups for steelhead. From this fact sheet, among the things I learned is that in the Southern Sierra Nevada diversity group, where the San Joaquin Basin is located, 6 watersheds currently have steelhead populations. But only one of these is considered to currently have the potential to support a viable steelhead population, or a Core 1 watershed. However, 6 other watersheds are considered candidates in the recovery strategy for hosting reintroduced populations of steelhead. And so I think one of the take-homes from this fact sheet and from many of the others was that we often find this place, when it comes to conservation of native fishes in California, that we're in a place of having tremendous work to do. We're also granted with significant potential to see progress. To realize this progress, it does take partnerships and a lot of teamwork. And that's why it's so important that all of you are here today. Next slide. I wanted to take a moment just to say a few words on who is here today. And this is all data that we got during the registration process. And Ted Flynn, one of the workshop organizers, provided these graphs. So we have a total of 241 total registrants for the workshop over the next 3 days or 2 days. 140 of you are from state and federal agencies. And then there are 100 of you that are from other types of affiliations, like municipalities and academia, NGOs, and private consulting firms. And next slide. Just under half of our registration group has specific steelhead experience. And the rest may not have maybe related experience or maybe not related experience, but have a general interest or general experience in fisheries. And so I think this graph right here gives you a sample that in this workshop, we are striking a balance between having the experienced and educated minds together with fresh minds, which is one of our goals. And then one final graph slide. You can advance, Brendan, thank you. I think it's worth noting that of the folks that said they have specific steelhead experience, we also have a mix of those working in areas of analysis, management, and monitoring. So really, really excited to have all of these perspectives together at this workshop, and particularly in breakout sessions, which, as Bruce already mentioned, are designed to be very interactive. Next slide. Finally, I want to acknowledge and really thank everyone that helped plan and is participating in this workshop. The planning committee had dedicated members from 6 state and federal agencies, the Metropolitan Water District, as well as you know, Bruce DeJaneiro from the Essex Partnership that's providing facilitation. We thank all of you from inside and outside the Delta that are presenting, and all of you for your active participation. Thank you. And next slide. I want to give a special shout out and thank you to your workshop organizers, Pascal Gertler and Ted Flynn of the Delta Science Program. They have fearlessly navigated the planning process with the planning committee since last September. They've worked really hard on this workshop to develop it in a way that's inclusive and representative of the varied input that they received through the planning. And as you know, as you're starting to get a sample of from Bruce's intro, that they've developed some creative approaches for interactive work with Mural. So we're really looking forward to the discussions. I also want to say a big thank you to the folks in the External Affairs and the Communications Division of the Council. Without you, we wouldn't be here. You're providing tremendous support through the workshop and technical assistance. So thank you so much. And without any further ado, I will hand it over to Josh Israel. And thank you. Thanks. We're so excited.
Thanks, Louise. Thank you, and thank Ted and Pascal for putting so much into this in particular. Let me see if I can pull up my slides. Let's see. Does this pull up something that looks like New Malonis Dam?
I can see your slide, Josh.
Okay, great. So again, thank you all for joining us today for the Monitoring Steelhead Populations in the San Joaquin Basin workshop. Reclamation is very excited to sponsor this workshop with the Delta Science Program to learn about successful steelhead monitoring programs on the West Coast and hear from innovative and state-of-the-science presenters about Central Valley steelhead. And most importantly, I think, receive your input during the breakout discussions. So let's see if I can advance it. Did it advance?
I don't see it advancing yet.
Nope, hasn't moved forward, Josh.
Okay. All right, hopefully now it's advanced to the appreciation slide. Does everyone see? Again, this is very similar to the slide that Luis had. Really appreciate all of the planning team's efforts, all of the presenters who are going to be presenting over the next 3 mornings, and finally, all of you, the workshop participants. Really, your participation is key to the success of this collaborative effort, and it sets the foundation for a partnership that we look forward to. I want to just take a moment to thank all of these folks again who have developed a really great agenda and fact sheets and breakout discussion format for the workshop. I'm really looking forward to the discussions I'm going to have this afternoon or later this morning with others. And most of all, just thank you for putting your time into this and committing your mornings and providing your input over the next 3 days for us to shape into the San Joaquin Steelhead Monitoring Program. So you've probably heard about the recent NEPA and ESA consultation on the long-term operations of the CVP and SWP, the reinitiation of consultation. This started in 2016, where Reclamation and DWR reinitiated consultation with NIMS and Fish and Wildlife Service, and the record of decision came out just about this time of year, 12 months ago. It's a very complex project that requires close coordination and collaboration with our federal and state and cooperating partners. One of the things that was identified was that there is a number of critical uncertainties, and to address this, we committed to ongoing advancements in science on a number of key topics, one of those including Central Valley steelhead. We hope that this science will help the agencies and public really better understand the status of ESA listed fish in relationship to the CVP and SWP's operations, gain new information regarding the uncertainty that impacts the flexible operation of the CVP and fish protection, and helps to refine operation capabilities of the CVP. We have 3 actions that we're taking related to steelhead. The first one is this workshop. Within 1 year, Reclamation is to sponsor a workshop to develop a plan to monitor steelhead populations within the San Joaquin Basin and or the San Joaquin River downstream of the confluence of the Stanislaus River, including steelhead and rainbow trout on non-project San Joaquin tributaries. And this workshop is our way of meeting that commitment to sponsor a workshop. Another ongoing investment that we have is developing infrastructure that will support a functioning life cycle monitoring program on the Stanislaus River and the Sacramento Basin CVP tributary to evaluate how actions related to stream flow enhancement, habitat restoration, and water export restrictions may affect biological outcomes such as juvenile and adult population abundance, age structure, growth and smoltification rates, and anadromy and adaptive potential in the populations that we study. And these efforts are starting in 2021 through a partnership with Kramer Fish Science, Fish Bio, California Department of Fish and Wildlife Service, and the U.S. Geologic Survey. And finally, Reclamation is continuing its San Joaquin Basin steelhead telemetry study in the lower San Joaquin River and Delta to understand how survival and route entrainment are affected by hydrology, operations, and other factors. And although last season, due to COVID, we were not able to do this study is continuing this year through a collaborative effort by Fish and Wildlife Service, National Marine Fisheries Service, and UC Santa Cruz. So finally, I just wanted to talk a little bit about the goals of the program. The objectives really of this workshop are to gather your input to inform the monitoring plan and the goals outlined in the plan. The monitoring program goals include estimating the juvenile and adult population abundance of steelhead in the San Joaquin River Basin. We also have a goal of monitoring to improve understanding of steelhead demographics. And then when combined with the other steelhead focused parts of our proposed action, such as the San Joaquin steelhead telemetry study, we hope to have information that will help to inform actions that will increase steelhead abundance and improve steelhead survival through the Delta. Again, I really appreciate you participating in this process with us and providing your input. We look forward to working with the Delta Science Program and planning team members to review the discussion that comes out of the breakout sections to help us develop the San Joaquin Steelhead Monitoring Plan. We're continuing to coordinate closely with other agencies related to the steelhead monitoring that is ongoing and expanding. And these future collaborations will help us hopefully further the goals of the San Joaquin Steelhead Monitoring Plan. And we look forward to working with agencies and stakeholders in the coming months and years on these collaborative opportunities so that we can implement and evaluate information from the plan to help us reduce uncertainties surrounding steelhead abundance and survival. So with that, I think I will pass it over to Howard Brown. Howard?
Thanks, Josh. Can you hear me?
I hear you.
Okay, good. Well, thanks, folks, for the your opening remarks so far, and I just want to kind of pile on to the extensive thank yous to, first the Delta Science Program. Pascal and Ted were so instrumental in pulling this workshop together in an incredibly short amount of time. I don't think I've seen such a comprehensive kind of pull together of presenters, topics, and kind of just really thoughtful structure going into a workshop or conference in such a short period of time before. So, without their support, this just couldn't have happened. And also to the steering committee members, a lot of personal, professional investment of time and thought that went into this. And, a major thank you to all the participants in the workshop. If I'd known that there'd be like 300 people signing up for this workshop and maybe 200 attending today, I might have proposed putting a volunteer sign-up sheet on the registration form, because we could probably pull together a pretty good steelhead monitoring program with this level of enthusiasm. But anyways, so I've been given the notable distinction of giving the regulatory context to the workshop. I'll try to keep it brief and to the point. Josh hit on some of it earlier with some of the elements of the proposed action, but I'll just pull it back a little bit to the original listing of Central Valley steelhead under the Endangered Species Act. So Despite steelhead being listed as a threatened species in 1998, there remain significant monitoring gaps that really complicate our ability to, understand the species abundance, its productivity, its trends over time, and it really also complicates management decisions. And I can't overstate that enough. I think that the complication of, a lack of good steelhead monitoring across the Central Valley really came to bear in the context of the recent consultation for the long-term operation of the Central Valley Project and the State Water Project. We had a lot of challenging conversations about, how to afford Central Valley steelhead effective long-term protections in the context of water management, which is complicated in its own right. So anyways, in those conversations during the consultation, I think one thing that really came out of it of the consultation was a commitment to advance the science of Central Valley steelhead. And we didn't do it just really out of the goodness of our heart, although to some degree I'm sure we did. But, really that decision to commit to advancing steelhead science, came out of the need to improve our precision to make water operations or water management decisions that, really brought, really affected good steelhead protections, right? So that's the first thing, improving our precision for water management to improve steelhead protection. The other one is to improve our understanding of steelhead response to habitat restoration. So integrated in the long-term operation plan are a lot of habitat restoration components, and we need to understand how steelhead are responding to these habitat restoration actions, and are they effective? Are they in the right places? Are we seeing population level responses? Are individuals responding as we would expect? These kind of things. So really hoping that over the long term we can do those two things: improve our precision to protect steelhead through water operations, and really effectively understand the species' response to habitat restoration. So Josh touched on some of this. There are really two kind of regulatory outcomes that came out of the consultation, and one of them was integrated, or a large part of it really is integrated into the proposed action, or the record of decision for long-term operations for the Central Valley Project and the State Water Project. And really we're here today to embrace one of those outcomes, which is the San Joaquin Basin Steelhead Collaborative. So really, the goal here, among many other goals, is to hold this workshop, is in a collaborative kind of partnering setting to help us inform the development of a monitoring plan that will be delivered to the Interagency Ecological Program for support, funding, and implementation. And then the other regulatory kind of component is from the NMFS biological opinion. There's a few conditions in the NMFS biological opinion. One of them really, the main one really focusing on accelerating monitoring and research for steelhead in the Central Valley, and with the goal of developing a juvenile production estimate, a methodology for evaluating a juvenile production estimate for a 4-year independent panel review that's integrated into the proposed action. And another component is ultimately to consider revising the incidental take limits for steelhead associated with loss at the Delta export facilities. So I think that's kind of the basic context here. I just want to add that achieving these lofty goals of monitoring steelhead in the Central Valley and the San Joaquin Basin for the purpose of really estimating adult and juvenile population levels can't be done by any single agency or entity, right? So that's really why we, put the term collaborative into the action that formulates this, or kind of led to the formulation of this workshop. NMFS can't do it alone. Reclamation can't do it alone. The state of California can't do it alone. Really, moving forward and changing the tone of advancing steelhead monitoring in the Central Valley is really going to require collaborative efforts and partnerships. And so I think one of the things that I and I hope others that that were on the committee for this workshop really want to encourage is thinking about how to establish partnerships where we can collaborate and work together to advance the status of steelhead monitoring in the San Joaquin Basin and the Central Valley. So with that, I'm really looking forward to getting into the presentations and engaging in the breakout groups later, and just want to say thanks again for folks for joining us today. I guess I'll pass it back over to Bruce.
Yeah, sounds good. Thanks, Howard. And I think in the name of time, I'm just going to move us right to our first presenter, which is going to be Greg. So Greg, looks like you're there, and I'll just pass the baton to you. Thank you.
Great. Thanks, Bruce. Can you hear me okay?
I can. Thank you.
Okay, good. Well, thanks everybody for joining, and thanks to the Planning Committee and for Howard for recruiting me to present to you today. You've got an exciting few days, I see from the agenda, some great fact sheets, and even more exciting will be as you enter the venture of moving steelhead monitoring forward in the Valley. Just a quick background, then I'll switch to slides. As I mentioned, I'm Greg Sieglitz. I work for National Marine Fisheries Service out of the Portland office, which is our West Coast region hub, and I work for the Interior Columbia Basin office. And like Howard, I also work on a large biological opinion, an EIS, and that's for the Columbia River. You may have heard of it formerly as the Federal Columbia Power System, or FCRPS, or now known as the Columbia River System. And that's a big part of what we do and what I do. I coordinate research, monitoring, and evaluation across the Columbia and Snake River. So I'm just going to give you a very high level overview to give you a flavor for what we do and what we know and maybe what we don't know up there, and an offer to continue the dialogue. As Luis and Howard mentioned around collaboration, we're very much into that up here, and I've already primed the pump with some folks up here in the north if that proves valuable for you all as you move forward. Let's see, so I'm going to share my slides now. Great. Can you see them okay?
Yes, but they're right now not in full screen.
We can.
All good? Okay, great. I'll just jump right into it. First thing I want to do is give thanks and notice to my colleagues with the Idaho Department of Fish and Game, Tim Copeland, and Oregon Department of Fish and Wildlife, Jim Rozicki, and many other entities that work on steelhead monitoring in the Columbia Basin. So as I mentioned, it's a big place, 1,200-mile long river, and 7 states and 2 Canadian provinces. For steelhead are not in all of those areas, and we do have significant blocked areas. I highlight in red here the large.
Greg, sorry, really quick to interrupt. It looks like you're only sharing the PowerPoint. You're not sharing the slides.
You're not able to see the slides?
It's not full screen. We're just seeing it as PowerPoint in general.
Okay, I've got it in slideshow mode.
Let's see, if you try clicking, do you have 2 screens?
I do not right now. Let me try closing this, and sorry about that. I thought we had this worked out.
It's all good.
I'll try again. All right, looks like I need to reopen it. Okay, is it in slideshow mode?
We're not seeing anything at the moment.
All right. Are you seeing a map of the Columbia River Basin now?
No, it's still just PowerPoint. It's only showing the first slide, but in normal PowerPoint mode, like when you're trying to edit it. If you want, I can try sharing the slides if you want.
Okay, sure. Maybe pull up the Columbia River Dam and map slide then. I'm not sure. It's advancing on my end, so I don't know what else to do there. So I'll stop sharing and then you will. Great. Okay. Thanks, Bert. So I was just mentioning the federal dams in red there, and we do have some public utility district dams on what we call the Upper Columbia in Washington in black. Go ahead and move forward. So purposes of monitoring in the basin, of course, are Endangered Species Act, evaluation of various major population groups, distinct population segments, for hatchery management, a wide variety of activities, including hatchery and wild interactions, the biological opinion compliance and action effectiveness of the federal family and their actions and work that's done by states and tribes and others under that. Certainly harvest management, we've got significant tribal, commercial, and sport fishing all along the river in the Columbia and Snake basins. Research and general population status and trends, and many other purposes. Next slide. I highlight here the tribal monitoring because that's a significant part of what happens up here in the Northwest. And on the theme of collaboration, there's a lot of collaboration that occurs between the states and the federal entities and the tribes do their own monitoring as well independently. I've in italics there are the tribes and tribal nations that do a lot of monitoring for steelhead. Others do other monitoring with less steelhead focus. Next slide. Of course, the state fish and wildlife agencies are significant contributors and actors in the steelhead monitoring world up here in the Oregon, Washington, Idaho in particular, and NIMS and our our Northwest Fisheries Science Center and U.S. Geological Survey as well. Next slide. So this is just a view of the Columbia River mouth looking west out to the ocean, and I'll start from there and kind of move upriver to give you, again, a high-level overview of the kind of things that we do. I didn't include anything about our at-sea sampling that the Northwest Fisheries Science Center does, but Brian Burke and company also do transects out there and occasionally run a steelhead, although they distribute widely and far. So in the estuary itself, next slide. There are some trawls that we do in the lower river, that is NAMP snow fisheries, occasionally pick up steelhead, often Chinook as well. Next slide. Move ahead, please. Next slide. So in the main stem, as we call it, this is Bonneville Dam looking up the Columbia River Gorge. It often offers opportunity, the dams that is, obviously habitat impacts and other things, but folks have fully utilized the opportunity they present for various pit tag arrays and handling activity. Next slide. In fact, in Bonneville Dam and others, there are fish windows that allow folks to actually count fish as they move through, adults and others. Next slide. Providing detailed information, even down to individual counts by day of fish moving up and down the river. Next slide. This happens to be Lower Granite Dam, which is on the upper end. Pit tags, as I mentioned, are installed in fish in hatcheries, on the spawning grounds, at traps and dams. Next slide. And at Lower Granite Dam, again, the uppermost dam on the Snake River, there's an antennas in the spillway that allow the detection of juveniles as they migrate downstream. Next slide. This is just a slide to give you kind of a feel for some of the information that we get from the dams. Individual numbers of fish moving through. This is kind of a comparison of the estuary trawl data. You can see it's many fewer of the fish, and then composition by species. Next slide. Obviously, hatchery operations, as I mentioned, provide another means of of tagging and marking fish, coated wire tags and others, and those are fully utilized in the Columbian snake as well. Next slide. Next slide, please. So now I'll move on to tributary monitoring. And if you all are not familiar with this, I'd recommend getting a copy of it. I can provide information to the planning team of how to do so, but it's the Untitled Field Protocols Handbook that was developed several years ago, kind of sort of out of the state of Washington, but a collaborative effort. Oregon relies on this heavily. And next slide, please. They've also created their own handbook as well, particularly for spawning surveys. That's Oregon Fish and Wildlife, and I can provide that as well. There's a link at the bottom, but if folks are interested. Next slide. So in Idaho and in Oregon both, the use of Weirs is a significant monitoring technique, particularly for adults. And I would say Idaho more so than Oregon, but both do use it. So of course you can use Weirs for spawning population abundance estimates. It's another opportunity to get your hands on fish and take various measurements, connect genetic samples, which I did not mention in the main stem, which is also another feature of actually collecting genetic material, particularly lower granite, which is a very key aspect of steelhead monitoring in Idaho now, because there's very little sampling that occurs in some of the tributaries to detect individual stocks. Hatchery strays, and of course, radio tags. Next slide. As you all know, steelhead are returning in the summer and overwinter, and then spawn in the spring. Next slide. And in Idaho, this can be particularly challenging, and so the use of Weirs has been, as I mentioned, an important technique. I'm just going to show you a few examples so you have a sense of it. These are more permanent structures at hatcheries, Rapid River, important area, and the Passamaquoddy. Next slide. Less so, not permanent, I should say, but temporary Weirs. On the left is the Chamberlain Creek, which is a unroaded area, roadless area, and very remote. So having lighter material and being able to backpack in is important. And then on the right, you see another area, Fish Creek, where there's more access, and you can actually use vehicles and whatnot to get larger Weirs in. Next slide. Part of the challenge with Weirs, though, is high flows in the spring, which is a common occurrence, can have their impact on these facilities. So next slide. There have been some other techniques developed, such as floating panel Weirs, that allow for more flood durability, and they can move up and down and withstand various events. Next slide. However, sometimes your monitoring device can become a restoration project, as in this coarse woody debris catchment. Next slide. So just to give you a flavor for this, the Idaho Department of Fish and Game, while they do depend on Weirs, many of the areas that steelhead spawn are remote. Many are wilderness or roadless areas. So you can see in total, we're only talking about 15 or so Weirs across the entire state. So it is an investment if you go that route, but very useful information. Next slide. So other techniques, of course, red surveys. You see a steelhead here in red. Next slide. But even that can be challenging. This is on the Lochsa River in Idaho again, and that area is an actual red because this is being done in the spring with snow melt and climate change withstanding. That can be very challenging to do red counts. Next slide. For juvenile sampling, of course, snorkel surveys is a common technique. This is one in particular that's been hit hard with COVID restrictions, just given the number of people that you need and in close proximity. So that's taken a hit this last year, but driving separate vehicles and using some other methods, folks have done some. But I will say that up here in the Northwest, we've definitely seen a decline in our ability to do some juvenile sampling. Next slide. Here's a crew installing a pit tag antenna array up in a tributary, which is a critical part of monitoring, as I mentioned before. This provides an opportunity to link information about juveniles produced in tributaries, migrating through the tributary corridor and rearing, and then as they move downstream, being detected again as they move through the main stem dams, and once again, upon return from the ocean, detected as well. But this is used in many areas in the Northwest. Next slide. Of course, screw traps, another method of capturing juveniles as they outmigrate to get an estimate on production and outmigration and survival in freshwater is another important technique that we use. Next slide. Hopefully you can see this represents the really the northeast third of the state of Oregon, or I should say a third of the geography of Oregon. Hood River area here is about an hour east of Portland for context, and then up here is kind of the corners of Washington, Idaho, and Oregon. You can see in red, that's the location of rotary screw traps for Oregon Fish and Wildlife, and I believe it was somewhere on the order of about 15 total. Next slide. So now I want to just mention sampling design a little bit. Again, this is a high-level overview just to start the conversation with us. So in Oregon in particular, and through some assistance through the EPA, they've developed a grit sampling design, which I'm sure many of you are familiar with. Generally, it's a random tessellation stratified sample. This is intended to create more of a representative sample across the landscape. But in doing so, you can stratify by removing areas that are obvious barriers to steelhead. So doing some initial work ahead of time and having some knowledge of the field and actually doing some field sampling and habitat availability is a critical part of the design. Next slide. We've also come to find that through a lot of sampling that reds have not been observed in gradients over 8%. And so that also is another aspect that could go into design development, characteristics such as that. Next slide. And you can go ahead and hit it a few times, Brandon, to go through these. This is just representing other means of stratifying. You can see this is about the source, transport, and depositional material for spawning grounds for reds in particular, and just depicting for you how you can go about stratifying on various habitat types. Ironically, in Oregon, in any way, they did not find that this provided much discernment in terms of predictability of reds, but it is one aspect of kind of laying out your sample. Next slide. Just again, showing you the grits as it's known, sample design, and this shows how, and this is the John Day Basin in kind of north central Oregon. It shows the distribution of their sites. There's a reference to the rotating panel, which refers to as you go back over time. I believe they're on a 5-year rotation. So the point is you would not hit these sites for a number of years until you would return, and allows over time to get a good estimate for the entire basin. And with that, I think I'm the end of the last slide, Brandon, and we'll entertain any questions and hopefully kept us on time despite our technical challenges.
Great, thanks. Thanks, Greg, appreciate that. So I think we'll just transition right to, let's see, to check my list. Who's next? Eric is up next. You out there, Eric? Maybe not, I'm not hearing you.
Can you hear me okay?
Yep, now I can hear you.
Oh, terrific, okay. Yeah, so let me try to pull up my slides and share here. It's the first time I've used Microsoft Teams, so bear with me. Okay, can people see the slide?
Yeah, yes, we can, thank you.
Okay, great. Okay, so good morning. My name is Eric Huber, and today I'm going to talk to you about the history of Central Valley steelhead hatchery management practices and describe how biocomplexity and biological portfolio effect strength has diminished over time. Before I begin, I would like to thank my collaborators who have generously volunteered their time for this unfunded research project. Stephanie Carlson and Rachel Ryan from UC Berkeley, Rachel Johnson from NOAA Fisheries and UC Davis, Robert Lusari, also from UC Davis, and Anna Sturek from the University of Essex. Okay, so what is biocomplexity? The EAC defines biocomplexity as the behavioral, physical, environmental, social, chemical, and physical interactions that affect, sustain, or are modified by living organisms, including humans. And today I'm going to be focusing on the biological interactions that are modified by humans. Next, what is the biological portfolio effect? Daniel Schindler, a leading expert on the topic, likens it to financial portfolios where diversification across assets reduces risks and stabilizes returns. Similarly, a wide assortment of diversifying features in biological systems stabilizes their performance. And I will be emphasizing the links between interspecific diversity and population stability today. This figure is from NOAA's recovery plan for Central Valley steelhead. It shows how interspecific diversity, namely life history diversity, genetic diversity, and metapopulation organization serve as the basis of population viability. Today, I will focus on how mykiss life history diversity enables salmonids to cope with environmental variation. First, a brief introduction to the system. Central Valley mykiss are propagated at 4 hatcheries. Moving north to south, there's the Coleman National Fish Hatchery, the River Fish Hatchery, the American River Fish Hatchery, also known as the Nimbus Fish Hatchery, and the McCollum River Fish Hatchery. The McCollum Hatchery is in the San Joaquin River watershed, whereas the others are in the Sacramento Basin. The Feather Hatchery was built most recently, and today I'll be emphasizing the period from 1970 to 2017, when all 4 hatcheries were operational. So on to our 2 main research questions. Question 1, how have Central Valley hatchery release strategies changed over time? And question 2, is there evidence for reduced biocomplexity and portfolio effect deterioration? We have 3 main research objectives. Our first objective was to investigate the temporal trends of release and return attributes from individual hatcheries and all hatcheries combined. Due to time constraints, I will only talk about the aggregated data patterns, but present overall mean attribute values for the individual hatcheries in the slides. And if audience members have questions and there's time about the individual hatcheries, I'd be happy to revisit the topic during the Q&A session. So here are the 11 different release and return attributes that we quantified. The release data up to the early 2000s were obtained from about 140 hard copies of hatchery annual reports for the American Feather and McCollum hatcheries. More recent data were obtained from electronic data sets provided by CDFW statewide inventory system. Data for the Coleman National Fish Hatchery were obtained in electronic form from the hatchery in the Regional Mark Processing Center. Crab return data were obtained from a variety of sources, including the statewide inventory system, the annual reports, the 2011 biological opinion for the Coleman hatchery, and McEwen and Jackson 2001. The basic reporting unit was a release group or cohort of fish of variable numerical abundances released together at a similar time, size, and location. And by making informed assumptions about spawn timing, emergence timing, and size at emergence, we were able to calculate release ages, sizes at age, and growth rates. Also, by making an assumption about the amount of time between release and return, we were able to calculate return rates. Due to missing data for the first 16 years of the 70-year time series, return rates for all hatcheries combined are available starting in 1964. Our second objective was to utilize the release information to assess population biocomplexity changes over time by calculating 10-year coefficients of variation for multiple release attributes. We also utilized the U.S. Fish and Wildlife Service's Chips Island Midwater Trawl survey data to determine the proportion of hatchery origin and natural origin mykiss present at the Delta Estuary Transition Zone. Our third and final objective was to evaluate temporal changes of biological portfolio effect strength by quantifying return rate buffering capacity by decade. Now the results. We observed a general decline in total number of fish released per year starting in the early 1970s. At that time, we see numerical releases ramping up as the Coleman Hatchery experimental release program became permanent and new hatcheries came online. Also note that the amount of fish released per year since the late 1990s is fairly consistent. We will revisit this later when I present the Chips Island monitoring data. We chose to analyze and display the data according to water years since the time period from October 1st to September 30th is more biologically relevant than calendar years. Unlike numerical releases, we see fairly steady amounts of total biomass released per year since the early 70s, with some dips and rises along the way. Here's a violin plot of annual sizes at release showing the probability density of the data at different values, and hash marks indicating mean values that are weighted according to the total number of fish released per release group. As expected from the increased allocations of biomass per fish, we observed a linearly increasing trend in average fish size. Also, release size variability has declined since the late 1990s. And for those of you like myself who think of fish sizes more in terms of lengths, here are the corresponding mean overall fork lengths at release for the individual hatcheries. The weight length conversion formula for Sacramento River mykiss from Halleck et al. 1961 was used to calculate fork lengths. As you can see, juvenile mykiss are released at relatively large sizes overall. Unlike sizes at release trends, we see that apparent ages at release have been fairly consistent over time. Slide in apparent age at release variability since the late 1990s. As expected from the size and apparent age at release trends, apparent absolute growth rates increase linearly for the first half of the time series before leveling off at approximately 0.3 grams per day for the second half. Overall, this corresponds to an average change in length of approximately 0.5 millimeter per day. Shifting apparent growth rate patterns have enabled hatchery managers to grow mykiss to smolt sizes within 1 year, which is a common practice at mykiss hatcheries throughout the Pacific Rim. Note that mykiss in nature typically require 2 years in freshwater to grow smolt sizes. Here's a figure showing how size-based life history stages at release have changed over time. The colors represent different stages that are named according to conventions outlined by the Interagency Ecological Program. The black circles indicate values for the dominance index, which is 1 minus the Simpson index and ranges from 0, where all life history stages are released in equal amounts, to 1, where one stage comprises all the releases. Overall, we see increasing dominance since the early 80s as the yearling smolt programs ramped up. Small smolts have been released almost exclusively since the mid-2000s. This is a violin plot for release timing. We see an overall shift towards earlier releases beginning in 1970. Also note the pronounced decrease in release timing variability beginning the late 1990s, which is consistent with the uniform production of small smolts growing at consistent rates and released at similar sizes and ages during this time. Here's a figure showing the distances fish were trucked downstream. We see that assisted migration distances have increased over time and that variability has decreased since 2000. While release location variability was also low during the first 15 years of the time series, releases at or near the Coleman and American hatcheries permitted fry and par to grow and morphologically diversify before exiting the Golden Gate. Here, we see that trapped adult return rates to hatcheries have increased over time. The overall rates are low compared to hatchery salmonids and other systems, even when straying rates and direct and indirect exploitation rates are considered. Larger fish, larger fish generally possess higher survival rates, and the increasing releases of smolt-sized fish likely contributes to the observed trend. Other reasons include changes in adult size criteria, from 22 inches total length to 16 inches total length in the mid-90s to mid-2000s. Increased trapping season durations may also be a contributing factor. Together with increasing return rates is increasing boom-bust dynamics in adult returns. We calculate that annual return rates have varied over 1 order of magnitude during the 10-year period between 2008 and 2017, Interestingly, we don't see the same dynamics at play from 1998 to 2007, which suggests that environmental conditions, in addition to release practices, might be driving the observed patterns. Here we show portfolio changes of key release attributes expressed as coefficient of variation values per decade. We see that system biocomplexity has diminished as a result of uniform methods of production and simplified release practices. In particular, we see a sharp decline beginning in 1998 when Central Valley mykiss were listed as threatened under the Federal Endangered Species Act. Here are the Chips Island midwater trawl survey data obtained from the U.S. Fish and Wildlife Service's Delta Juvenile Fish Monitoring Program. Since brood year 1998, the propagated Central Valley mykiss have received it. This enables fisheries researchers to discriminate between hatchery origin and natural or wild origin fish. We see a highly significant linear decline in the proportion of wild fish present at the Delta San Francisco estuary ecotone. As you may remember, total numbers of hatchery fish released annually have been fairly consistent during this period, which suggests that absolute numbers of wild fish in the system have declined significantly. Hatchery fish appear to dominate the system, comprising over 90% of the standardized catch at Chips Island from 2010 to 2019. Putting it all together, we see that the differences between aggregate stock return rate variation and constituent stock return rate variation are declining over time. The deterioration of buffering capacity is coincident with releasing fish in large numbers at restricted times, sizes, and locations, and is consistent with the expectations of biological portfolio theory. Increased coupling of population dynamics, combined with the reduction of wild fish in the system, may be driving the recent boom-bust behavior, at least during periods of environmental instability, such as that which occurred during the recent drought. So in conclusion, the Central Valley mykiss population complex is expressing declining biocomplexity over time as a result of simplified hatchery release practices and the apparently increasing proportion of hatchery mykiss in the system. We observed that biological portfolio effect strength has declined over time, as evidenced by reduced variance dampening and population stability, and exemplified by recent boom-bust return rate dynamics. The reduced diversity and stability is expected to impair population viability and make the Central Valley mykiss population complex less resilient to environmental variation and change. So that's it. Thank you for your time and attention. And if there's time, I'd be happy to answer some of your questions.
Thanks, Eric. I think we're a little tight on time, so I'm going to ask if you do have questions, you can put them in the chat and we can try to address that. And I know there were some sound issues with Eric's presentation. I'll try to mention, if it gets too bad, I'll let the speakers know. It's a little intermittent there, but thank you, Eric. So I'm going to just keep moving and turn it over to our next speaker, Mariska. I hope I got your name pronounced correctly out there.
I am here. Yeah, I'm going to try to get my slide shared.
Yep, we're seeing it.
Are you seeing it? And let me get it into presentation view and see if that works. Come on. All right, are you seeing the presentation view?
No, it's still in slide mode.
Dang.
Oh, wait, there you go. You're
Yay. Good. Good. All right, great. Well, thank you for inviting me to talk about steelhead monitoring in the Russian. I want to just say how much I applaud what you guys are doing. Holding a workshop while you're developing your plan, that's such a smart thing to do and something I wish we had done 8 years ago when we were starting our CMP monitoring. So the work that I'm going to talk about today has been a partnership with California Sea Grant, Sonoma County Water Agency, and the Department of Fish and Wildlife. So the California Coastal Monitoring Plan came out in 2011, and this was written by Department of Fish and Wildlife and NOAA Fisheries, with the high-level goals of tracking status and trends for coho, chinook, and steelhead in coastal California streams. And the idea was to have a more standardized sampling approach with a common database. And there are basin-wide and life cycle monitoring components to this plan. So Fish Bulletin 180 is our guiding document. You can find that online. And then we also have a plan that's more specific to the Russian River. So just for context, the Russian is about a 1,500 square mile watershed, over 1,000 miles of stream, and home to 3 listed species of salmon, coho, chinook, and steelhead. And I think one difference probably than a lot of the streams you guys are working in is that it's not snowmelt driven. So the hydrograph is much more tied to rainfall. We have really high flashy flows in the winter, and then a receding hydrograph over the summer to, in a lot of tributaries, just no flow at all during the summer. And then lastly, it's almost entirely privately owned land. So our first step in implementing the coastal monitoring plan was to develop a sample frame. And so we needed to define habitat for coho, steelhead, and or chinook. We started with a GIS exercise, so using the NOAA IP model. And then because for this plan we were interested in anadromous habitat, we applied the pad layer to exclude any stream reaches upstream of barriers to anadromy. And then there was a lot of just pouring through habitat reports and consulting with local biologists to refine that sample frame down to what we thought was representative of habitat for these 3 species. And we certainly did not get out and ground truth our entire frame. We're kind of doing that as we go. CMP uses a grit sampling approach so that we can collect random spatially balanced samples. And in our case, we needed to divide our frame into 2 to 4 kilometer segments. That was our unit for sampling, but it could be any kind of, it could be point sampling, it could be different size reaches, whatever you want to do. In our case, it was 2 to 4 kilometer reaches. So basically, you divide your frame into these reaches, and then you order them from downstream to upstream, starting with the main stem. So you number up the main stem, then you go back down to the furthest downstream tributary, and then the next tributary up, etc. And then once you've numbered them, you conduct a sample draw, which adds that random component. And CMP uses Trent McDonald's software for doing this. So basically, in this little 10 reach sample frame, we have our frame number. Can you guys see my cursor when I move? I can't tell. We have our frame number, and then you have this randomized draw order. So each reach gets this randomized number. And then you go through the exercise of assigning whether each reach has, we're talking about steelhead, whether it has steelhead spawning habitat or steelhead juvenile habitat. So if it has that type of habitat, it gets a 1. If not, it gets a 0. So in this case, in this little mini frame, we have spawning habitat in the main stem and just in this lower order tributary, but then not in the upper reaches, and then juvenile habitat everywhere. So how do we make use of this frame? So in our, for CMP monitoring, one of the main things that we're looking at that we're trying to estimate is the abundance of reds in the entire basin. So we want to estimate how many reds the Russian River are produced in the Russian River each year. So we sort our reaches according to this draw order from lowest to highest. And then if we're going to go out and do steelhead red surveys, we're not going to be able to necessarily sample the whole sample, every reach in the sample frame. say we can do 3 reaches. We would then pick the first 3 reaches that are going down the draw order list. We'd pick the first 3 that have steelhead spawning habitat, and we'd go out and we'd do those surveys. We'd estimate a red density for each reach. We'd average that across the 3 reaches, and then we could expand that out to the 6 reaches that have steelhead spawning habitat in our frame. So then in the summer, we might be interested in looking at juvenile production, and maybe, snorkeling is a little less resource intensive than red surveys. So say we can do 4 juvenile reaches in the summer. We'd pick the first 4 according to our draw order, which means we'd sample reaches 5, 8, 7, and 6. And then same idea, we'd calculate a juvenile density for each of these 4 reaches that we sampled, expand out to the 10 reaches that contain juvenile habitat for our basin-wide estimate. And then one of the nice things about this GRITS approach is that if you're going down your draw order list and you come across a reach, in this case, reach 8, say there was a fire, you can't go survey there this year, you can skip it and you can go on to the next reach in your list, and it retains its spatial balance. So in the Russian River frame, we have 472 reaches. 418 of those are steelhead. Coho, we have 106, much more confined to the lower part of the basin. And then we have 80 Chinook reaches. We're talking about steelhead today. So here's a map of all of the steelhead habitat within our frame. And like the example I gave, one of the main metrics of interest for CMP is the total number of reds and ultimately adult spawners produced in the entire basin every year. So we do these spawning ground surveys, Gallagher protocols, and we only have the resources to do 30 of those reaches every year. We can't, which is actually a pretty low percentage of the 418 reaches in our frame. It's just a little over 7%. So how do we pick what reaches we're going to do? We're going to use that GRITS framework, but we're also going to use a rotating panel. So our goals are both status and trend. So for trend detection, a good approach is to just use kind of the traditional index reach or index stream approach, where you go to the same place year after year and you can detect trends really well. But for status, it's much more important to have better spatial coverage. And so that's where rotating panels can come in. They can balance those 2 goals of status and trends. Here's an example of the 30 reaches that we surveyed in a given year. And with the rotating panels, we have a set of reaches that we sample every year. We have another set that we sample every 3 years, and another set that we sample every 12 years. Here's what that rotating panel looks like in table format. So you have 1 panel of 12 reaches that we sample every single year. We have 3 panels of 9 reaches each that we sample every 3rd year. And then we have 12 panels of 9 reaches each that you sample every 12th year. So in a given year, we're sampling a total of 30 reaches. 12 of them are ones we sample every year, 9 are ones that we sample every 3rd year, and 9 are ones that we sample every 12 years. So each year, we're sampling 30 reaches, but they change over time. And then after the 12-year cycle, we will have sampled 147 unique reaches. So where are we at? We've been doing these basin-wide estimates for steelhead for 3 years now. We are getting these estimates of reds, very high confidence intervals. Not too surprising given our low sample rate of 7%, but they're very resource intensive, and so that's a constant challenge. And then I also just wanted to show this map. Even though we're collecting these high level metrics, we're also collecting this really fine scale data on red locations by species within each of the reaches that we survey, and that's been really important for some of the recovery activities that are going on. I'm going to shift gears now and talk about the life cycle monitoring, which is kind of the second major component of CMP. So the idea is that within each CMP watershed, you have your basin-wide monitoring, and then you also have a life cycle monitoring station, a watershed where you're looking more intensively, you're monitoring more intensively to look at fish out or abundance of juvenile outmigrants, fish in or number of adult returns, freshwater and marine survival, spawner to red ratio. So that's a metric that the idea is that will support the basin-wide monitoring. So we're getting estimates of reds for the whole basin, but most resource managers would like to know the number of live adult returns. And so the idea is that in a life cycle monitoring station, you estimate how many live spawners are returning, as well as how many reds are in that life cycle station. And you develop this ratio that you can then apply to the entire basin, to your red estimates for the entire basin. And then lastly, these life cycle stations are places for diversity monitoring. So looking at life history strategies, age structure, spatial structure. We do a lot of research specific to management questions or recovery actions in these watersheds. So for our program, we started with this large life cycle watershed, Dry Creek, because it had steelhead, coho, and chinook, but we ran into a lot of issues with being able to generate these core metrics. And so a few years into it, we actually switched our life cycle monitoring station to be these 4 smaller streams, in part because they already had life cycle monitoring infrastructure in place because of the coho, a separate coho monitoring effort. So some of the methods for life cycle monitoring, counting stations are a key one. These can be traps, Ptag antennas, video, Didson. We've tried all of these. And those are where you're estimating abundance, survival, and migration timing. Then we do the red surveys in all of the reaches within the life cycle streams. And we also do juvenile snorkel counts. These are primarily done for coho, but we're incidentally counting juvenile steelhead as well during those surveys. So I'll just touch on some of the challenges. So just starting with fish out or juvenile production, how many juvenile steelhead are migrating out each spring? And we had been running these downstream migrant traps for years, primarily for coho, never catching very many steelhead smolts. And we really kind of presumed they were leaving a lot earlier. And that was the case. We started doing some pit tag monitoring on one of our streams, and this graph is showing the distribution, the average proportion of steelhead out migrants over the course of a rainy season, and in relation to when we're able to run our traps. We have very, very flashy systems, so it's not possible to safely run those in the winter. And so we, in fact, we were really missing anywhere from 55 to 5% of the steelhead outmigration if we were going to rely entirely on traps. And so we, kind of knowing this, we decided to take a different approach to estimating steelhead outmigrants. We had these paired pit tag antenna arrays on 4 of our streams. We wanted to take advantage of that. And so we decided to try estimating fall abundance using a modified basin-wide visual estimation technique, or Hankin and Reeves. So we snorkel each of the 4 creeks and map out the distribution of juvenile steelhead young of the year. And then part 2 is going in and electrofishing a fraction of the pools to both calibrate our snorkel counts, but then also to get pit tags out. So we're tagging these fish in proportion to how they're distributed throughout the creeks. And then now that we have these pit tagged fish in the creek, we want to take advantage of the paired pit tag antenna arrays and use those to estimate the probability of these pit tagged fish surviving over the winter and emigrating the following year. And so we estimate that probability, we multiply it by our fall abundance estimate, and that gives us an estimate of outmigrants. And yes, steelhead are messy. They have many, many, many different life history strategies. So not all of them, we can't assume that they're all leaving in 1 year. We're hoping that over time with the pit tag work that we'll be able to account for some of these different life history strategies in our fish out estimates. So we've really only been able to do this for 1 year so far. We were able to get our fall abundance estimates and then the probability of surviving and emigrating, which we used to estimate the number of outmigrants. I don't have a lot of time, I think, so I'm just going to touch briefly on some of the methods we've used for getting the number of adult returns or fish in. We've tried adult trapping with resistance board weirs. We don't have dam facilities with fish traps, so we've had to try out these resistance board weirs, video monitoring, and DIDSIN. And I guess after trying all of these things for several years, I can say that all of them work some of the time and none of them work all of the time. So it's really a challenge to come up with one method for getting at adult returns. With traps, you saw a lot of the pictures earlier, in the Russian system, the majority of steelhead and coho come in on these atmospheric river events when they can easily swim around a trap. We've also had, issues with fish like this coho getting stranded on our weirs. So those have been actually the least effective of the things that we've tried. Video monitoring works really, really well until it's turbid, which is almost every time it rains. So we get partial fish in using that technique. And then DIDSIN is great at counting large fish in really high turbid flows. But in our system, there's a lot of overlap in adult migration timing with the 3 salmonid species. So it's really hard to determine what species you're looking at on the DIDSIN. And then we also have a lot of really big suckers and pike minnow in the system, so that confounds things even more. So we're kind of back to the pit tag antenna approach. In these 4 life cycle streams, we have year-round pit tag antennas. So we're starting to get juvenile steelhead tagged, and we're hoping that we'll be able to detect enough of them returning that we can come up with adult estimates, but it's too soon to tell at this point. And we're, I think sample size could be a real issue with that approach. So fish-in has been a little bit of a struggle in terms of estimating actual spawning fish, but we have been pretty successful at generating red abundance estimates. So we do these red surveys in the life cycle streams. We've been doing that for a long time, and we're getting estimates of reds. And so that's a good, adult metric to look at. It's just we haven't kind of cracked the nut of developing that spawner to red ratio so that we can translate these red estimates into estimates of adult returns. So just really quickly to wrap up, this work is definitely a work in progress. We've been, successful at generating some of the estimates. We have basin-wide red estimates. We are still working on trying to translate that into adult estimates of adult returns. I just wanted to point out there's a lot of other really neat metrics you could use with the grit sampling frame. Juvenile occupancy is one that we've been doing for coho. That's been a neat one to look at. And then again, I'm not going to go through everything here, but we've had some good success with fish out and partial success with fish in and survival. We're just kind of waiting to see how the PTAG approach works with adult returns. And then one thing I didn't get into is we are learning a lot about steelhead life history strategies, and the PTAGing approach is going to be really useful for that. So yeah, that's all I have, and there's a ton more to talk about, and I know I would have loved to have had these sorts of conversations when we were starting out. So I know everyone on our team would be happy to talk to anyone if you have questions about specific techniques or just want to brainstorm ideas. Thank you.
Wonderful. Thank you so much. So we're running a little behind on time, but I did see there was a question about use of drones and whether you considered that for red survey. Maybe you can answer that briefly while Devin maybe gets ready for her presentation.
Yeah, we would love to use drones. Our issue in the Russian is that so much, almost all of the land surrounding the streams is privately owned. And there's just a lot of, you need to get permission to do that. And so I think we would love to do that. I think it would be really a useful technique, but that's our limitation with that.
Great, thank you. And I noticed there were some others responded to the question in the chat. I'm still catching up, clearly. Okay, so again, in the name of time, I'm just going to move right into Devin's presentation. You out there, Devin?
Yeah, I am. I'm here.
Excellent.
Switch that, I think, while I'm talking. I don't need to hear it through the headphones. And what do I do here? Share tray. What do we see in here?
We see your slides. Thank you.
Okay, perfect. All right, well, a little bit about how to present this talk today and what would be useful.
Devin, really quick, sorry to interrupt. If you could, at the top left corner there where it says swap displays, you're right now showing presenter view. So if you click on that button at the top, it says swap displays.
Did that work?
Yep, there you go.
Okay, great. So yeah, just trying to think about what would be most useful as a workshop. And I decided that I would start with just a little genetics 101 so that all the language that I'm going to use in the talk is clear. I'll go through a few slides and a couple of examples to talk about what we mean when we talk about ancestry and adaptation and looking at genetic data. I'll then, of course, highlight the two main life history variation questions that have been coming up in steelhead and mykiss, that residency anatomy, and then this run timing variation between summer and winter steelhead. And then at the end, I'm going to try to present kind of a framework for how you might think about what this data means for management in Central Valley steelhead, and hopefully that will be useful to people. So just to dive in quickly to some language, I'm going to talk about a locus. A locus is just a region or a location in the genome. Sometimes it's a gene. And a lot of complexity can be hidden within that, but think about it as just a single variant in the genome. And then, since I know you've all been paying attention to the variants of COVID that are circulating in the world, a way of thinking about this further is that alleles at a single locus are those variants. So you might have two different variant types at a particular locus, and they're going to spread throughout populations based on not their infectiousness, but their ability to survive, reproduce, and essentially their fitness in that population. However, unlike COVID, in most animals, these alleles are combined in individuals into genotypes. So an individual can have 3 genotypes. It can be a homozygous for either of those alleles that are there, or it can be a heterozygous. And so that's our basic genetics right there. And what geneticists use to understand populations and individuals is the distributions of these alleles and genotypes, essentially their frequencies in different populations or their distributions in individuals. And we can think about this as dividing it into 2 different things. Although, again, that kind of hides a whole lot of variation that's important to understand. But looking at ancestry, population relationships, parentage, pedigrees, that kind of thing, we use one subset of loci, essentially loci distributed throughout the whole genome. We're going to try to use lots of loci. And we're going to assume that these things are neutral. That is, they're not under selection. And so their distributions will reflect the gene flow and ancestry of those populations. And in contrast, we identify particular loci in the genome that are functional, that are associated with a particular trait. And we refer to this as adaptive genomic variation and think about the adaptation of this and how that affects its distribution among populations and individuals. And so, since everybody can relate to dogs, I thought I'd start with a dog example. This figure is a way of representing genomic data. So every dot in each of these panels represents a single locus in the dog genome. They're arranged by color or different chromosomes. And their height in each panel represents an association of that part of the genome with a particular trait. So the middle panel is drop ears, so it's just a droopy ear trait. And you can easily see that there is one locus there and a number of others that stick up quite a bit higher than all the rest of the genomic data. And these are hundreds of thousands of loci distributed throughout the dog genome. And that is a way that we can identify what particular parts of the genome are associated with a particular trait. It's important to recognize, though, as that example sort of hinted at, that adaptive genomic variants, they're not all the same. They're quite variable. There's essentially a continuum from neutral variation to strongly adaptive variation. So some traits that we look at, in fact, we often assume that most traits are polygenic. They're going to have many genes that are associated with them. Other ones, like some of those dogs traits that I just showed, are almost single locus, or a single locus of major effect controls a large portion of the variance in that trait. And that's a genetics concept called penetrance that describes the strength of the effect of a particular gene on a phenotype. And the other part of the variance is going to be due to environmental variation or other genes besides that single locus of major effect, of which, again, there may be quite a few. So to start with a fish example, this is now a few years old, but it was one of the early ones that came out with a very strong example of life history variation in a salmonid. This is Atlantic salmon. Here's a similar figure to what I showed you before, and you can see that almost all the genome, all the chromosomal dots there are below that horizontal dotted line. And there's one locus, VGL3, that really jumps out as associated with the trait that they looked at, which was age of return, not spring versus fall, as we might look at in Chinook salmon or something, but in whether they come back as 2-year-olds or 3-year-olds, very similar to what we might look at in steelhead. And what was striking here was that these 3 genotypes are here, and if you have one variant, the early variant, fish tended to come back as 2-year-olds. If you are homozygous for the late variant, fish come back as 3-year-olds. And then those heterozygotes displayed one more trait a genetics term that I need to teach you is dominance. And that is how the heterozygote phenotype is compared to the 2 life history reps. And what's interesting in this particular example is it was sex-dependent dominance. So heterozygous males tended to look like the early phenotype, come back younger. Heterozygous females tended to have a phenotype much like the late homozygotes, came back as 3-year-olds, which is advantageous for them. They grow larger and have higher fecundity. So this was considered a single gene of major effect. There's been a lot of follow-up work on it. But in terms of how much of it explains, they found that it explained about 39% of the variance in this trait of age of return. So its penetrance was actually not that large. 60% of the variance is still unexplained by that. So that's an important thing to keep in mind when you're thinking about these types of examples. Yep. So let's move into steelhead, and the trait that I think is a focus for today is looking at anatomy versus residue, whether an individual matures and becomes a steelhead and goes to sea or stays in fresh water, and what kind of genetic basis there is of that. There's been a lot of work on that over the last 20 years or more, and this list is not inclusive. So a lot of research has been done to understand this. And what's really clear from that research is two things. One is that it is polygenic. There are many loci throughout the genome that are affecting this in different parts of the range. And these are environmentally dependent effects. There's a lot of elements of growth rate and other aspects of the juvenile development that will influence this. But the other thing that's clear is that there's one region on chromosome 5, one chromosome in the genome, that contains essentially a single locus of major effect for this trait. And that's what I'm going to focus on next. So this OMI5 region, however, as I hinted at, it's not a single gene. It's a large region. It's structural variation of the genome that's held together by an inversion, which is just a structural part of the genome of that chromosome. So it's 50 million DNA base pairs long. It contains over 1,000 genes. But nonetheless, because of that structural combination, we can think about it as a single locus of major effect, the same as the other things that I've been introducing. So it has two variants, an A type, which is the ancestral. It's more similar to other salmon species, and this rearranged type that is unique to mykiss, and that we associate with the resident phenotype. And I'll talk more about what I mean with that. So individuals, again, we can think about it as having three genotypes, homozygous for either of those types or the heterozygote. And in a data set that we were able to analyze from a coastal population, we can see that there's this very strong pattern of difference in how individual phenotypes. So this is detection probability of looking at smolts migrating out of the system and coding them by their genotype. And we see, like that Atlantic salmon example, there's a sex-dependent dominance pattern. So in females, homozygous for A or heterozygous are much, much more likely to be detected migrating out of the system than females from that same group of individuals that were tagged that are homozygous for the other haplotype, the resident genotype. Whereas in males, the heterozygotes appear to be more like the resident homozygote. And that sex-dependent dominance allows both sexes to sort of optimize their strategy, since females benefit much more from becoming anadromous. It's important to note that this is just one example in one system, but these data are consistent with a lot of other data that has been collected in different systems. At the same time, we also showed that there's a very strong climb in the frequency of these two different haplotypes as you go north. So down here in California, frequencies tend to be intermediate. You see populations that are mixed and have all three genotypes present, and we see that association with migration. Farther north, we don't have good data on the individual migratory movements, but we know that in many populations of steelhead, so these are below barrier populations, some of them steelhead hatcheries, they are fixed, and meaning they have no variation in this region, and they only have the resident haplotype. So clearly up there, other regions of the genome are having a strong effect on that migratory decision, or environmental effects are having the majority influence there. So let's switch gears and look at run timing variation in steelhead. So this is now a completely different phenotype, but one which also has a gene of major effect. And so the research on this has been much more recent, but papers are coming out quite quickly and increasing our understanding of how it's distributed. So in run timing, we're looking at a much smaller region. There's I refer to it as a GREB1L region. That's a gene that's in the region. There are actually a couple of other genes in that region as well. And I'm not going to talk about which ones are the most important points in that genome. But again, think about it as a single locus of major effect that's associated with run timing and return timing of adult return for summer and winter steelhead. So like the other examples, we can think about there being three genotypes that are distributed in the populations. I do also want to note on this one that although this is a much clearer case of a single locus of major effect than with OMI5, there's not a lot of evidence for other genetic variation associated with this trait. There is evidence that, for example, in the Columbia River, that it may behave quite differently than what we've seen in coastal California. so that there are likely to be environmental or lineage-specific effects or variable penetrance in sort of how strong the effect of this gene region is on this trait. And that's important to keep in mind. There's very little information on the Central Valley specifically. So if we look at the distribution of variation of these three different genotypes in different populations, we see some very strong patterns. So this is an array of populations. I just chopped off the names because they were a mess. But if you focus in on ones where I've highlighted with a yellow arrow, those are sort of pure or canonical summer run steelhead populations. And you can see that they are essentially fixed. Have 100% of the individuals have that SS, that summer homozygote genotype. And conversely, the populations with the blue arrows are very strong winter steelhead, coastal steelhead populations. And they have nearly complete presence of the winter run homozygote in those populations. But in a lot of other populations here, and I'll highlight a few more in the next slides, are intermediate genotype frequencies, and all the genotypes are often present. And one thing this highlights is that ancestry and adaptation, these sort of two concepts that I'm describing, can be quite decoupled. So in this more traditional population network here, I'm showing relationships derived from microsatellites and SNPs, again, neutral genetic variation. These population relationships are going to reflect primarily geography and gene flow between populations. And so geographically close together populations are next to each other here. And what you see is that the summer steelhead populations are distributed throughout this, in each case, closely related to the fish that are in the same river with them. And yet, as I just showed, those same populations have completely different frequencies of GREB1L genotypes. So there's a decoupling there between ancestry and adaptation. Another way in which we can see this is in populations that are sort of isolated or disjunct from other populations. So with GREB1L, we're talking about run timing in steelhead. But what happens when fish with that one variant or the other are above a barrier like a waterfall? We don't necessarily know. So these two populations I've highlighted are above waterfall barriers in Middle Fork eel. They presumably have ancestry from summer steelhead and then have inherited the summer steelhead GREB1L haplotype, but they're above waterfall barriers and are completely fixed for that resident OMI5 haplotype. And they're clearly rainbow trout that are above a barrier. So how we want to consider and think about these different adaptive variants when they're interacting and at very disjunct frequencies is something that's important to consider. And then the last one of these I wanted to mention is, since we're talking about primarily the Central Valley and the San Joaquin system, several of these populations in this figure are from the Central Valley, hinting at or supporting this historical presence of summer steelhead in those drainages. In particular, a number of these are above now dams, like in the American River, above in the Clavey River, in the Upper Tuolumne, and are showing quite high frequencies of genotypes associated with summer steelhead run timing. The below barrier hatchery populations that I have included here have all three genotypes present. So we clearly have some of this variation present in the Central Valley, regardless of, and it would be interesting to look at more thoroughly in terms of return timing of different populations in steelhead. Nimbus there, you can see, has a much higher frequency of winter run alleles, and that would be interesting to look again how that's expressed. So I tried to think about how to present this in terms of what it means for conservation and management. How should or can we incorporate this into conservation and steelhead management in the Central Valley? And I think the best way to think about this is that like the phenotypes that they're associated with, these adaptive variants are going to reflect the ecological conditions that they encounter and the resulting relative success, relative fitness of individuals with different phenotypes. So if the habitat is present for a particular phenotype, and its adaptive genomic variation will also increase. An interesting aspect of this is the assortative mating that is set up by the habitat separation, and I'll show you what I mean in these next few slides. So this is kind of a cartoon representation that I came up with to think about how the genotypes are going to distribute themselves on a landscape. So if we think about a typical coastal California stream with no barriers, you're going to have OMI5, let's start with that, genotypes distributed throughout that system. Some of those individuals, all those genotypes are going to migrate, others are going to stay in the watershed. And the relative success of those will depend primarily, in this case, on the habitat that's present in that system. If it's very good for residents, you may have a relatively high frequency of resident haplotypes and therefore resident phenotypes. we introduce some structure to this system, you can see that there's immediately going to be some shift. The lower reaches may still have a relatively even distribution of these genotypes. But as you move up in the watershed, ultimately to a waterfall barrier that has only one direction of gene flow possible, you're going to start losing those more migratory associated genotypes. And as we see in almost every case above waterfall barriers, we see an enrichment of the resident haplotype and ultimately to fixation. So we can apply the same thinking to looking at the summer and winter genotypes. But the important distinction here is that these are all steelhead. And so what we're thinking about here is flow-dependent barriers and how they might be dynamic over space and time. So you might imagine that in some scenarios and some systems, you have these partial barriers stepping up into the system, leading to one that is only accessible if you return early. And so then above that barrier, you're going to tend to have genotypes and enrichment of genotypes for the summer steelhead haplotype. And other genotypes, winter and heterozygotes, may end up below that barrier. But as these are variable and dynamic in space and time, there'll be other years perhaps where high flows or changes in the geomorphology of that system, whether they're natural or anthropogenic, cause more mixing. This will then lead to additional production of heterozygotes and resegregation of those genotypes throughout the system. That doesn't mean that selection isn't continuing to act and segregate these things, but it will be variable over space and time. We may also have something like a landslide that comes down and prevents any steelhead from surmounting that final barrier. The earlier migrating genotypes will then be forced downstream where they may have different fitness outcomes, but they're going to mate and reproduce with the individuals that they encounter there. And then remember, as I showed, this leaves an open question of what is remaining above that barrier, above that landslide, and and how they may contribute to the gene pool once that landslide erodes and access is restored there. So these different adaptive variants are going to interact when they can. And of course, I would be remiss to give a talk like this without talking about dams and how those are somewhat different from the type of system that I just described. When dams are put in place, they separate populations of trapped fish that are above that dam, and then they block access from below so that the below barrier population ends up as a mixture of resident and adamant steelhead below. They also create reservoirs above them, which is quite different from a waterfall system. And so as a result, they can potentially retain neutral and adaptive genetic variation above them. And of course, this is a major factor to think about in the Central Valley system. So going back to my cartoon landscape, if we drop a dam into place and create a reservoir, we're going to initially trap the genetic diversity that was present in that mixed steelhead and resident population above it. And we've seen now in a number of studies in coastal California, San Francisco Bay Area, and Central Valley systems that A variant, the anatomous associated variant of OMI5, is present and retained above reservoirs, likely due to adfluvial behavior, migratory behavior in those reservoir populations. We still may have an enrichment of resident haplotypes in further upstream things that are above further barriers, waterfall barriers. But the retention of that adaptive genetic variation is quite clear and common. And I also wanted to highlight that a recent paper that just came out on looking at this exact thing at both OMI5 and Greb1L genetic variation following the Elwha dam removal, and showing the contribution and interaction between steelhead and resident trout in that system. So just to conclude and kind of come back to what I've been saying is that this adaptive genetic variation is different than the variation in the way that we think about variation associated with ancestry, but it's maintained by evolutionary processes of relative fitness of different genotypes. And so the diverse and dynamic habitats that steelhead and rainbow trout and that mykiss inhabit are strengthened by having this portfolio effect of diversity where these different populations can interact, support each other, and have partial segregation in some cases. For monitoring purposes, for the ancestry of Sacramento and San Joaquin steelhead, that depends on population genetic and parentage data analysis, the types of things that we've implemented at a number of hatcheries in the Central Valley and that could be implemented in monitoring programs for wild populations as well when appropriate samples are available. This adaptive genomic variation provides additional tools for that. But I want to leave one final thought. If you only take one thing from that, it's that these individual genotypes do not perfectly predict phenotypes. So I've often been asked, oh, hey, we have some tissue samples. Can you genotype OMI5 and tell me if these are steelhead or not? And I hope that I've explained that you understand that like, we can't really do that because there are other factors, including environmental and growth factors, that go into ultimately determine the phenotype. But what we can do is look at the distribution of those genotypes in different populations, and we can predict what the most likely phenotypes and genotype associations will be. So if you give me a large adult steelhead, I'm going to bet that it's a female, and I'm going to bet that it has an AA genotype. But I can't tell you that with certainty. Well, I included this slide because I felt like I hadn't said enough about Central Valley steelhead ancestry, but this is from a publication that Carlos Garza and I did a few years ago. And if we have time where people want to ask questions or have follow-ups, we can sort of discuss the issues that were raised in that paper around ancestry and relationships among Central Valley steelhead populations. But I felt like it was more important to describe this framework of adaptive genomic variation. And that's all I had for you guys today. Let me know. I can't see anybody or tell if there's any questions.
Great. Well, thanks, Devin. That was really interesting. And I did notice there's a few questions in the chat, and because we're a little short,
no, I can see that.
maybe if you don't mind, Devin, taking a look at those, and you could just put some answers in the chat. I think people
absolutely.
That.
Yeah.
That way we can address the questions without necessarily taking up more time here. So we have one more presentation. We're about 10 minutes behind. So what I'm going to suggest we do is go ahead and move to Will. We'll do it, as quickly as you can. If we run a little bit over, it'll just cut into our break a little bit, but we'll still reconvene at 11:30 into our breakout group. So we'll talk about that when Will's done, but I just wanted to put that marker out there. So it looks like, Will, you've got your slides up, so I'll stop talking and let you take over.
Perfect. And is this in presentation mode? Look okay to people?
Yep, looks great.
Great. So I'll be talking about some state-dependent life history models that some collaborators and I developed over a decade ago now, but I think it's still hopefully relevant to this meeting. It may hopefully point out some of the key demographic parameters that might be most important to monitor as you're developing monitoring programs, and potentially also identify factors that management might want to change if it turns out that the model tells you that the current demographic conditions in a particular location are not particularly favorable to anadromy being an evolutionarily selected or persisting strategy. So I did this work while I was a postdoc with Mark Mangle. Several other people, including at least a few who are on this call, made significant contributions, including Mike Beeks, Sue Sogard, Joe Mers, Rob Titus, and Sean Hayes. And so the approach we took was really sort of a mechanistic approach to life history modeling. So this sort of contrasts with a lot of other studies that have looked, across space and looked at what systems do they see anadromous steelhead in, what systems do they see resident rainbow trout in, and sort of tried to correlate what are the environmental conditions that favor one versus the other. We sort of took the approach of, can we predict from first principles whether we would expect to see anadromy and or residency in different systems based on certain environmental factors and how they relate to demographics. So from sort of a life history theory perspective, we just tried to identify what are the factors that would select for residency or select for anadromy. And so some factors that could create selective pressure in favor of fish maturing as residents would include that they can avoid most likely higher mortality rates in the ocean as opposed to fresh water. It's potentially also easier for fish to spawn repeatedly if they take the resident life history. Conversely, selection might tend to favor individuals that smolt and emigrate when they're able to grow to much larger sizes in the ocean, which would tend to lead to higher reproductive success. You can also ask, if fish may take either an action to mature in fresh water or an action to smolt and go to the ocean, and why would a fish take either of those actions when it's young versus old? And so, life history theory might predict that you would tend to take, or selection would favor taking actions when fish are young, because there is then less cumulative risk of dying before the fish is able to take that action. Conversely, there could be selective pressure to wait and take those actions at older ages. In terms of spawning, it gives fish time to grow to larger sizes, which may lead to higher reproductive success. And in terms of fish that are smolting, delaying emigration to an older age likely leads to larger smolts who likely have a higher probability of surviving their emigration and their time in the ocean. So we developed a model algorithm that's based around a sort of assumed trade-off between growth and then ultimately size and fecundity versus mortality. We postulated the existence of decision windows that were in advance of the actual physiological transformations that fish had to undergo. Our model assumes that fish assess their current size and potential for future growth if they remain sort of uncommitted par during these growth windows, and also assess what's the expected fitness of fish who either smolt or mature, depending on what the decision window is, at their current size. And then the model compares what's the expected fitness of taking that action now versus the expected fitness if the fish waits and grows to a larger size and then makes an optimal decision in the future. Of course, that future fitness has to be discounted for the mortality that is expected to take place between the decision window and that later action. The model I'm going to present today is currently developed for females, since there's sort of a clearer link between size and reproductive output. But a lot of the same logic applies to males. There probably is at least some extent of a reproductive advantage to larger males also. And also just want to point out, so we're not in any way asserting that fish are actually making these kinds of calculations or making conscious decisions. But really, the prediction is that natural selection should tend to favor fish who, through the genetic and developmental mechanisms that are available to them, tend to follow the life histories that this model says would be optimal under different conditions. To put this in sort of equation form, so we developed a dynamic state variable model where for fish we track their expected lifetime fitness, that is their expected number of eggs produced, as a function of their size, a developmental switch that says whether or not they are on the pathway to sexual maturity, a developmental switch that says whether or not they have initiated the smolt transformation, and then just track this through time. We need to establish a function that says how fish grow from one time step to the next. And we need a function that describes how fish survive from one time step to the next. We can then assign fitnesses sort of starting by working backwards from when spawning actually takes place. So for a fish that has adopted the anadromous life history, or sorry, for a resident trout that has reached sort of the maximum possible age, this capital T, it receives fitness that's based on a length-dependent fecundity. For a resident fish that spawns at an earlier opportunity, it receives some immediate benefit from a size-dependent fecundity, and then plus the expected fecundity it would have from future spawning events, assuming that it survives to that time. We can also assign fitness to emigrating anadromous fish, which we do assuming there's a length-dependent survival function, and then a typical reproductive output of returning steelhead, which, in our case, we factor in what's the sort of expected size at first return, what's the fecundity at that size, and then also what's the probability of repeat spawning, and then adding in some discounted fecundity for the possibility that steelhead may spawn multiple times. Outside of decision windows, we can update the state-dependent fitness of fish based on their current state by simply calculating what's the probability that they will survive until the next time step, and then what's the fitness that's associated with the size they're expected to grow to at that time. And then during each decision window, we can assign fitness by maximizing over decision. We sort of assume fish will behave optimally in the future, and so at each decision window, we can assign fitness based on different life history trajectories and states based on what the optimal decision is we identify with our model. This picture is partly to just provide a little break from equations, but also to point out there's quite a bit of variation among individuals. So these are two fish collected on the American River at the same time. We believe these fish to be of the same age, and yet they are quite different sizes. And so, one might imagine that the optimal thing for these fish to be doing over the rest of their life cycle may be a little bit different, since they are quite different in their state. And so the required inputs to our model, and so things that would be great to monitor if you're developing a monitoring program and you want to know whether conditions are favorable for anadromy in a system or not, include survival. So survival in freshwater, survival during the migration process, and survival in the ocean. For our purposes, we used primarily literature values and then did sensitivity analyses, since these were some of our most uncertain parameters. Just pointing out, the way the model is structured, survival can vary by season within freshwater. We also need model inputs that describe growth. You can either just sort of have a simple growth rate that's determined external to the model, or for one of the papers we wrote, we tried to model growth rate using an energy balance and optimal foraging theory based model, which I won't go through this equation in detail, but basically we have temperature dependent consumption ability and also temperature dependent metabolic costs. And then there's also, we track availability of food in the environment, and based on how available food is, fish need to exert different activity levels to get varying amounts of food, and then there are costs associated with that, which are also temperature dependent. In our case, we took the temperature dependencies and the allometric relationships here from the literature. We got some information on gut capacity and basal metabolic rate from lab fits. And then food availability, something that in theory one might monitor, although it's hard to necessarily translate, say, drift samples into what fish are actually experiencing. But again, food availability could be something to monitor if growth rates are hard to monitor directly. And the model also requires inputs that describe fecundity. In our case, the size and egg production relationship. You could also think about maybe secondary factors like egg size or red quality, and then also the occurrence or frequency of heteroparity. Some things that definitely are important but are not currently model inputs include, there's some literature on the direct effects of temperature on the smolt physiology. We didn't try to model direct behavioral responses to flow, to temperature, or to the density of competitors, and we didn't really look at cascading ecosystem responses. And in part because a lot of the great work Devin just talked about was not published at the time we started on this model, we didn't do any explicit modeling of heritability or genetic constraints, but that could be something very interesting to explore in the future. And of course, you all can probably think of a lot more things that we didn't put in this model. But we're hoping that the sort of growth survival trade-off captures a lot of what's going on. And so our model produces a suite of outputs that are both direct outputs and then more sort of emergent or more complicated outputs of the model. Directly, the model will predict whether fish smolt as a function of their size and growth rate in a given environment. It also predicts maturity as a function of either size, or in the case of the youngest fish, the date on which they emerged and their recent growth rate. And it also predicts not just what the optimal decision is, but what's the relative fitness of taking one pathway versus another. And so that sort of says something about the strength of selection for one life history pathway over the other under different conditions. There are also some emergent predictions, because for each size and growth rate, we're predicting whether or not fish will smolt. We can identify a threshold sort of above which we predict smolting and below which we don't. By looking at a distribution of individuals with different sizes and growth rates, we can predict how, just life histories might be distributed across a population, what fraction might express one life history or another. By parameterizing the model based on environmental conditions for different areas, we can predict geographic variation in life histories. And then we can also make projections for the future of what might the selective and demographic consequences be if environmental changes lead to differing demographic rates in the future. As a first pass at trying to validate this model, we parameterized it for 3 study systems. Scott Creek is a small coastal stream near Santa Cruz, where I'm based. And then the McCallum River is, as I'm sure you all know, in the sort of very northern end of the San Joaquin Basin, and the American River in the Sacramento Basin. These habitats vary quite a bit in their growth rates they support. So on Scott Creek, it's a pretty small and relatively food-poor system. Fish grow relatively slowly there. Fish grow substantially faster on the McCallum and faster still on the American, where we were seeing fish reaching 30 centimeters in their first year of life, which seems to be some of the fastest mykiss growth we know for anywhere. And so, we parameterized our model for each of these systems and made the predictions of state-dependent life histories for each. These first sets of graphs show what are the predictions of whether or not fish would mature during that first maturity decision window based on the date on which they emerged on the x-axis. So the earlier they emerge, the larger they will be on a given date, and then how fast they're growing on the y-axis. And note that in all three graphs, we have some bands of red, which are the combinations where we expect that fish will mature, and some bands of white, which are areas we predict fish will wait until their next decision window. And then within each of these plots, we've put, just sort of roughly speaking, these rectangles with a black outline show what's the rough range of emergence dates and growth rates we saw in the field. As we can kind of see for Scott Creek, we saw essentially no overlap between the range of sizes and growth rates with the ones in which we predict maturity. But if fish were growing a little bit faster than the fastest we saw, we would predict some of them would mature. Contrast that with McCalmey, where most fish are in this weight area again, but it's actually in this case some of the later emerging or slower growing fish that do overlap with the red. And so it's actually in this system, the slower growing or later emerging fish we predict would mature. And then on the American, again, we have essentially all fish in the area where we predict they wait or not mature. And so, overall, that predicts little to no residency on Scott Creek or the American River versus some residence on the McCalmey. We also have make similar plots of decisions predicted for the smolting decision window. So we have Scott Creek on the top and the McCalmey and the American. And here, blue is combinations of sizes and growth rates for which we predict fish will smolt, and white are areas where we predict that fish will wait. And again, we have these rectangles, and in the case of Scott Creek, these lines for older fish that sort of show what are the sizes and growth rates we tended to see. So on Scott Creek, pretty much all of the 1-year-olds were in this area where we predict that they would wait. 2-year-olds, quite a few were in the area where we predict they wait, but some were large enough we predict they smolt. And then essentially all 3-year-olds were large enough we predict they smolt. For the McCalmey, we had, again, a mixture where the smallest fish would be predicted to wait, but most fish would be predicted to smolt at their first opportunity. And on the American, sort of all fish were so big and growing so fast that we predict essentially all of them would smolt at their first opportunity. One other thing to note, if you compare across these different systems, this white area, is always on the left, saying that the smaller fish would tend to wait. But note that the white area is larger for the American and the McCalmey than it is for Scott Creek. So you're sort of essentially, we're predicting a larger size threshold for smolting in these Central Valley systems where growth is faster. And again, we're predicting that smolts, to the extent they occur on Scott Creek, would tend to be older, whereas smolts on the McCalmey and the American would tend to be younger. And then one other thing we can do is not only identify what is the optimal life history, but also say what's the fitness associated with taking suboptimal strategies as a function of size. So here we're looking at the sort of the first smolting decision window. What's the expected lifetime fitness of a fish that takes the anadromous life history pathway over a range of sizes? That's the dotted line. Versus what's the expected lifetime fitness for a fish that takes the resident pathway? That's the solid line. And note on the American, these lines are far apart over this entire range, so we would predict fairly strong selection anatomy in that system. Compare that to on the McCalmey, where again, for sort of the mean size fish, which is this dot, we do predict higher fitness for anadromous fish. And there is some distance between these lines, so there's some selection here for anadromy. But if you look at the smaller fish, the dashed line and the solid line are quite close, suggesting essentially very weak selection for what younger fish do, and then potentially for smaller fish. And so we might expect a polymorphism, especially on the part of smaller fish. To sort of quickly, our attempts at model validation to date have generally showed that the model seems to do a pretty good job, although not perfect, of predicting what we see. So we do indeed tend to see mainly older anadromous fish on Scott Creek, although there certainly are some residents there also. This may be complicated some by migration in from above waterfall resident populations. We do indeed on the McCalmey see a mix of both resident and anadromous trout. And at least, in the sampling we did, we saw essentially only anadromous fish on the American, and some scale reconstructions from returning spawners suggested that the vast majority of those did in fact leave at age 1. Of course, there are alternative explanations one might offer for all these geographic patterns we saw. As I mentioned, we predict a larger size threshold for smolting in the valley versus the coast. And in some lab experiments that Mike Beeks led up, we did indeed see that Central Valley source fish had to be larger to survive a saltwater challenge in the lab. And then we've also done some work tracking the individual life histories of marked fish in Scott Creek, which did seem consistent with larger fish being more likely to smolt. We certainly did see smaller fish moving downstream also, but it seemed like a lot of the smaller fish were making use of a productive estuary habitat to grow faster in, but then several of the smaller fish that we saw entering the estuary then moved back upstream later, whereas none of the larger fish that entered the estuary were seen again. Some sort of future directions or elaborations of this model that might be worth pursuing. Certainly, refine functional relationships between temperature, flow, food, and growth rates would improve the modeling of growth rates in different habitats and be, I think, very helpful in trying to make system-specific predictions and predictions about the effects of environmental changes or changes in water management strategy. So this is where I think a lot could be done to predict management effects on life history by more refined models and even just data on growth and survival. And a couple examples of papers that have done that. Benjamin et al. Tried to apply this modeling framework in the Columbia River Basin and try to predict life histories under various climate change scenarios. Dave Botten and colleagues have applied this to, I believe, the Santa Ynez River in sort of Santa Barbara County. Everything I presented so far has assumed that there's sort of a deterministic yes/no knife edge response to being above or below a threshold. I think, probabilistic reaction norms where you have state-dependent probabilities of different life histories, but not simple step function responses might be more realistic. And then certainly I think bringing in some of the evolutionary dynamics and explicit genetic inheritability considerations that Devin brought up, could certainly be helpful in refining and advancing these models. With that, I'd like to take any questions if there's time. Also should acknowledge that most of this work was funded by CalFed back when CalFed was a thing.
Great, thanks, Will. And I'm going to ask if folks have questions. It looks like there are, I don't see any new questions in the chat, but please go ahead and put your questions in the chat and I'll ask Will to look at those, only because I want to make sure you all have some time for a break. I know we've been at this for a little while and there's lots of great information, but a lot to digest, and I'm sure everyone could use a restroom break and maybe a little food or whatever. So the plan is this. Please leave your systems on if you can, because what's going to happen is we're going to take a break, and then when you come back, you will be sorted into breakout groups. So this is going to happen automatically. Brandon is going to wave his magic wand and send you off randomly into breakouts. And so if you leave your machine on, you'll get sorted, and then when you come back, you'll at 11:30 to your desk, you'll be in your breakout session. And so I'd ask everybody, I know we went about 15 minutes over, so you only get 15-minute break instead of a half an hour break, but ask everybody to bear with us there. And please do come back at 11:30 for the breakout sessions. We will go till 12:30. I apologize, I said 12 earlier. We are going to go till 12:30. So we'll have 11:30 to 12:30 for breakouts. And you'll have a facilitator and a note taker in each breakout, and they'll walk you through what we want to try to accomplish in the breakouts. So, and thanks to those that are already populating the workshop mural board. That's great. I see some good things showing up there already. So thanks for doing that. Let me just ask Brandon, Pascal, anything that I forgot to mention here that you want to mention before we let everybody go for 15 minutes?
Nothing for me.
Okay. Sure, great. All right, so thanks everybody. We'll see you back here at 11:30. Once the breakouts are over, we're done for the day. So we won't come back to plenary, and then tomorrow I'll share out a synthesis of the different breakouts, and we'll get into the next day. So thanks everybody, and we'll see some of you back at in my breakout at 11:30. All right.